Hello and welcome to our Lakeside chat. We are David Wofford and Katie Noonan, co-chairs of the Rotary Nature Center Friends. And we're so happy that you can join us tonight.
As we begin our program, it is important for us to acknowledge that we are on stolen land, that Lake Merritt is part of Ohlone territory. We hear now from Corinna Gould, spokesperson for the Confederated Villages of LaShawn and co-founder of Segura Te Land Trust.
Good afternoon, relatives. My name is Corinna Gould. I am the spokesperson for the Confederated Villages of LaShawn. We are here today at what most folks think of as Lake Merritt. We are in the territory of Huichin. Huichin is actually a territory that encompasses 6 Bay Area cities: Oakland, Berkeley, Alameda, Emeryville, Albany, and Piedmont. And so this is a place that my ancestors have been since the beginning of time. And this was a place of abundance. I'm so happy that people from all walks of life that now come into our territory can enjoy this beautiful place that my ancestors have enjoyed since the beginning of time. My relationship to the land that I have been born to, raising my children and grandchildren here, has been to tell the story, the truth of what happened on this land before other people came here. I'm hoping that as we begin to learn these lessons of fires in California, the pandemic that's happening, that human beings come back to living in reciprocity with the earth.
We are very excited to invite Dr. Jere Lipps to talk about climate warming, the world, and Lake Merritt tonight. He's has an interest in geology since he was a child of 6, and it just went from one opportunity to another with him to increase his knowledge and then to share it with others. And Jere, we really thank you for being here tonight. So Jere, are you ready to begin?
Yes.
Thank you so much for being here.
My pleasure. So I wanted to talk to you about climate warming. I've been working on that problem since I first started working on the California Channel Islands in Ice Age deposits. We were looking at different levels of ages of fossils, and some of them were warm water and some of them were cold water. So I got involved in this climate warming business very early, and I continued to talk about it in all of my classes at the university. That would be UCLA, Davis, and Berkeley. So the first thing is that climate is a very complicated thing. It's really involves the entire world. And without that perspective, we can't really understand what's going on at Lake Merritt. And this is one of the problems, I think, that people have with climate change. The other problem is the anti-science, anti-climate change attitudes of various people, that climate change is a Chinese hoax or just a hoax in general, and that I am incompetent and I conspire. That's not true, but I want to warn you that what we will see in this talk is the evidence that they don't ever deal with. They deal with other things: politics, capitalism, sometimes religion, and other things that have no place in a scientific discussion. And that's what we're going to have here tonight. So here is a view of the warmest year, 2024. And you can see that it is ranges from about a little less than 0 change to about 6 degrees change from the average of 1951 to 1980. So it's been warming up, and this is the warmest ever in recorded history. And it's the warmest of the last 5 years or so. The arrow shows where Lake Merritt would be, and it is not in the darkest colored area, which is up around 4 to 6 degrees change, but in a lighter area where we see it a lesser change. And all of this depends on different characteristics of the atmosphere and the oceans, as well as the terrestrial configurations that we have. So I do this mainly for my grandchildren. It's not going to affect me, but it's going to affect my grandkids, my great-grandkids, and all of my family from now on will be impacted by the things we're talking about tonight. So I think it's very important to keep that in mind, because nobody objects, I hope, to impeding their families in the future. Even some of our politicians should agree with that. So what's the problem? Well, there's nature, the sun, and then there's us spewing various sorts of things into the atmosphere, represented by that airplane down at the bottom. So what changes climate? Well, over millions and millions of years, mountain building and ocean movements, the currents, the geographic setting of these things impact the climate big time. And we've had in the geologic past, going back a billion years, times when there was very, very warm and other times when it was very, very cold. In fact, even with a snowball Earth, where the whole Earth was frozen over. But we want to deal today with the last three, volcanism, which when a volcano goes off, it spews a sulfur and CO2 into the atmosphere. The sulfur, when it's predominant, can lower the temperature of the atmosphere. CO2, of course, is a greenhouse gas, and that'll warm it. And the other two, the Milankovitch cycling, sets up the stage for us and shows us how the climate has varied and sea level has varied over thousands of years, about 1 million years for sure. And then lastly are the greenhouse gases, CO2 and so forth. So let's start with Milankovitch cycling. And you can see on this diagram all those letters at the top were supposed to fly in at different time, but it's not set up to do that. So let me just focus on the diagram. This is the Milankovitch cycles. They are caused by gravitational attractions or space-time fluctuations in the solar system, mainly Jupiter and Saturn. And so that changes three different things that we'll talk about in a moment. But let's take a look at what it really does. Up at the top, you see present day sea level, the wavy line. And you'll notice that it says it's warmer and higher. So on the left, it's warmer in temperature up in that direction. And the sea level is higher up in that direction. At the bottom of the graph, you can see that it's 780,000 years old, going up to zero, where we are today. And it would be colder and lower sea levels in that diagram. Now, the other thing to notice here is that at this point, underneath the writing, is 125 to 120,000 years ago, sea level was exceeded, the present day sea level, by about 8 meters as glaciers melted. And then underneath this writing is the present day sea level. So out of the last really million years or so, those are the two times that we've been warm as it is today, and with sea level at or above that level. Everything else has been lower. So Milankovitch cycles are caused by the attraction of these different kinds of things. So axial tilt changes the tilt of the axis so that the Earth's surface receives more radiation. which warms it. And that works on a periodicity of 41,000 years. It repeats. And then the eccentricity of the orbit, so that it moves maybe from a more elliptical orbit to a less elliptical orbit, again, changing the amount of solar radiation. And that periodicity is 100,000 years. And then probably the most important one, at least that we can see in the geological record, is precession. This is the periodicity that's caused by a wobbling of the Earth, and the wobbling of the Earth's axis as the Earth goes around in its orbit creates winter at different times in that orbit and summer at a different time. And you can see on the right-hand side of that diagram, the first, does that arrow show up? Anybody see an arrow going around? I guess not. Okay, so the right-hand diagram under precession shows winter in the top diagram being on the left, and then in the middle, it's at the middle of the bottom of the orbit, and then finally winter at the other end of the orbit. And this precessional periodicity is 23,000 years. So combining 23, 100, and 41,000 years creates the Milankovitch cycles. We call them Milankovitch cycles because a guy named Milankovitch, he was a Serbian, came up with this and discovered all of these things long ago in the early 1900s. And so we knew about what the Earth was doing then, and eventually it got plugged into the climate. Now, this diagram I show you is the last part of that Milankovitch cycle, starting back 150,000 years ago. And the temperature is along the left-hand side. And the diagram, again, shows sea level, present-day sea level, as the dashed line across the middle at about the 60-degree temperature. And it shows then the swings in sea level as you move from left to right. You go from the last interglacial 150,000 years ago, 125,000 years ago, excuse me, to the last glacial time when the glaciers were everywhere on the continents and sea level was well over 400 feet lower than it is today. And then it begins to warm up, and glaciers on land, including Greenland and Antarctica as the big contributors, began to thaw out and release not just the meltwater, but ice into the ocean. So a glacier that goes rolling down into the ocean, every bit of ice that falls into the ocean also increases the sea level. It's not just the meltwater. And that's something we have to think about, the collapse of some of these major glaciers. So we go up here to the present day sea level. And on this diagram, even in 1970, the guys who put this together noticed that there was a carbon dioxide induced super interglacial. And they suggested that that was going to go off in this direction and bend over and come back down. It's getting so warm that my thought is it's just going to keep going. It'll get warmer and warmer and warmer, and we'll never go back into a lower stand of sea level or cooler environment. So this is the sea level rise in the last 20,000 years. And let's just start over here on the left-hand side, the last glacial maximum. And that was the low point on that diagram. And then all these little check marks are different data points from which the compilers of this diagram used. And I've covered up all the sources of those so I could point out some of the things that were happening. So I want you to look at this part, the line next between 14 and 12. That represents 13,000 years ago. And I'm going to show you what that looked like in a little while. And then as sea level rose, it eventually rose up to the mouth of the Golden Gate. And the sea then was at the Golden Gate. This was prior or after the sea had been offshore some 50 kilometers or so, well beyond the Farallon Islands. And I'll show you that too. And then as that slope of filling of the bay continues, because it's now beginning to fill it up, about 4,000 years ago, the sea filled San Francisco Bay, which had been a series of river valleys, one from South Bay, one from North Bay, and all of its tributaries, and flowing out through the Golden Gate onto the shelf. And at the same time that the San Francisco Bay was formed about 4,000 years ago, so was the spot where Lake Merritt originated. Here's the picture that I wanted to show you. You can see on the left-hand side, the 13,000-year-old shoreline beyond the Farallon Hills here, but those are the islands when sea level starts rising. So 13,000 years ago was also significant because the Bering Land Bridge was exposed during this period and earlier, so that humans were able to cross from Asia into North America. And we know that they were down along our coast about 12.8 thousand years ago, because we have that date on a site on San Miguel Island. So people may have been living along this coast that is now underwater. We have no record of it because it's been destroyed or just simply not discovered. And then at 8,000 years, shown in the middle of the diagram, the 8,000-year shoreline is mostly the present coastline and a little blob of water through the Golden Gate, but not into the bay. Sea level rose in another 4,000 years, enough to fill up North Bay and South Bay and the tributary that led to Lake Merritt and all the estuaries that we have along the East Bay. I'll return to this diagram later. So the people came down, the humans arrived probably around 13,000 years on this coast. We know also, you've probably heard about the footprints at White Sands in New Mexico that date 22 or 23,000 years, human footprints. I think they've straightened out all the problems they had with radiometric dating. So it may be that humans were able to cross the Bering Strait earlier, certainly sea level was low enough, and that they migrated down into the central part of North America earlier than they did along the coast. Or maybe we just didn't yet find these older sites. And then they have old sites down in Mexico and down all the way into South America. So the first humans that arrived 13,000 years ago, if we assume they did, we don't know anything about them to speak of along our coast. But at 8,000 years, we know that there were milling stone people that had campsites and villages in the area. And about 4,000 years ago, the present day Ohlone tribes people appeared in the record. So they appear about the same time that the estuaries in the San Francisco Bay filled up with seawater. So I just point that out as a coincidence, and probably they were walking alongside the water as it moved along. Okay, so that takes care of Milankovitch, sort of. Let's talk about what is global warming. Let's start with 3 terrestrial planets in our solar system, Venus, Earth, and Mars. They're all greenhouse planets. What does that mean? They all have gases in their atmosphere that tend to warm the planet. Venus and Mars atmospheres are 95% carbon dioxide. Earth's is just a few percent carbon dioxide. Venus, being closer to the sun and volcanically very active, is just loaded with CO2, and its temperatures range between 700 and 800 degrees. The Russians landed a lander on Venus, and it sent back a few pictures and then burned up. On Mars, the atmosphere is also around 96% carbon dioxide, but the temperature is minus 61. What's the difference between Mars and Venus? Well, Mars is much smaller. It may have had a much heavier atmosphere in the past, and the geologic evidence looks like it also had a lot of water. But all of that's gone now, and the atmosphere has been pounded by solar radiation, and it's much thinner. It's only 1/100th as dense as Earth's atmosphere. So this very weak atmosphere, even though it's 95% carbon dioxide, it can't warm the planet. But on Earth, as I said, we have quite a variable delivery of CO2 through geological time, and now we're changing it a bit that I want to tell you about. So these greenhouse gases, I'll show you a list of them in a moment, are trapped in the atmosphere, and then they trap heat. And it's contributed by volcanoes, human activities like cars, coal-fired plants, burning things, and some other sources like agricultural sources, permafrost. As permafrost melts, it releases another greenhouse gas, and nature simply can't remove it fast enough. The removal of it would involve a chemical reaction with the Earth's rocky exposures. And it affects both the atmosphere and the ocean. They are both linked, and they are both warm. So we already found out that water vapor is the most abundant greenhouse gas, but it doesn't stay in the atmosphere very long. It rains out in a week or so, let's say. And so it really doesn't contribute too much. The big contributors are carbon dioxide and methane. Carbon dioxide lasts in the atmosphere for 300 years. So our current day value of CO2 will be with us and be added to in every day in the future for 300 years. I don't know how we're going to get out of that. Methane is more powerful as a greenhouse gas than CO2, but it only lasts 12, it varies in estimates, 12 to, I've seen 70 years. And then these other 3 are not considerable contributors. So we're really going to focus on carbon dioxide and methane. So we measure carbon dioxide in 2 different places, or have, I should say. And this graph shows the 2 different methods or sites, their methods as well. So from before 1860 to 1958, we got the CO2 values from ice cores in Antarctica and I think in Greenland too. And this was done by drilling down so that they knew the age, so that they knew when they were at 1860. And then they could take the bubbles in the sea ice and analyze them for CO2. And then they constructed this part of the curve on the left-hand side. But a better way of doing that came along in 1958, and people down at Scripps set up a carbon dioxide measuring observatory on Mauna Loa in Hawaii. And you can see that it's a fuzzy line because that represents a seasonal fluctuation in CO2, but you can see that it goes up quite high. And today it's 427 parts per million. I looked that up for you. Let's take another look at this. Here it goes back to it's about 1700, and you can see it was pretty much the same, 280 parts per million CO2, and then it begins to move up in the 1850s. And then as the Industrial Revolution gets going, it jumps up again and continues in 1900. It crosses into about 300 parts per million, and then it takes off like crazy as Industrial Revolution, automobiles, airplanes, ships, and all the other things that we do, especially generating electricity, also generates CO2. Now we've got 427 parts per million in our atmosphere in 2026. So it's a good starting point for the next year. We'd start right here in January at 427 parts per million. And I should point out that 2 days ago, it was 428. It fell down today a little bit. So where does all these energy-related CO2 emissions come from? You can see on this graph, which was made in 2012, how much CO2 was emitted at particular points in billions of metric tons into the atmosphere. When the study was done in 2012, they measured 32 billion metric tons. They also projected 43 billion metric tons in the year 2040, shown at the bottom of this graph. And the 37 with the yellow line is today. So it's now 37 billion metric tons of CO2 in our atmosphere, and it's projected to go on for quite a long time. So here's some of the effects of greenhouse gases in the atmosphere. You know, as you mess around with the atmosphere, lots and lots and lots of things change. It's not just that it's getting warmer, it's changing the patterns of currents in the air, changing the temperature of the ocean from top to bottom. It's changing how fast ice melts. It's changing all sorts of things. So it increases H2O because as the atmosphere warms, it holds more water. So it increases rain and flooding. We see that every damn year. The South gets flooded out, and then the East Coast gets flooded out, and then we get flooded out, and it just continues to repeat itself. And then we have an increase in the El Nino events. That's a thing where the ocean, Pacific Ocean, slows down. The El Nino kind of wipes out upwelling along our coast, and the ocean warms up. That then contributes to the temperature distributions in different ways. So it increases overall the temperature range from 6 to 12 degrees C. And as I've shown you, sea level rises up to 8+ meters or 27 feet, 125,000 years ago. Because the oceans are warmer, greater hurricanes occur, maybe more numbers, and certainly greater intensity of them. Because CO2 chemically reacts with the ocean, the oceans become acidified, and that impacts the organisms that live there. And then all of this difference in the atmosphere and the ocean redistributes the crops that we use and the species that we use and see in the oceans. When I first got into this climate thing, I looked at the CIA had a paper on how they were planning on changing the crops that they could grow in Russia. And they would not be able to grow wheat in Russia because it'd be too warm. And this was a big deal for CIA. Anyway, I thought that was kind of interesting that the CIA seems to know what's going on. And then, so there's major changes in the ocean, and along with that, the biota, particularly coral reefs. We don't have any of those around here. The nearest one is at Cabo Pulmo down in Baja, California. It's kind of a beat up old reef, but it also is suffering, and we'll see how that works. So let's look at warming. Here's the Berkeley Earth summary of warmth going back to 1750. And the gray patterns on here showing around the Berkeley Earth summaries are errors. So naturally, they didn't have very good record keeping or even instruments from 1750 shown here up until about the almost 1900s. And then the air bars go away, and then you can see how the temperature has risen off to the right from about -1 or 1.5 to +1. That's a big deal, you'll see. So I mentioned how the atmosphere changes because of the distribution of heat. And this map shows the winter distribution of heat. The Western United States is usually very warm, and off into Canada, it's very warm. And over here in the eastern part of our country, they're freezing their buns off from 0, less than 0, up in the northern part, all the way down into Tallahassee, where my friend there just sent me an email, said it was -2. That seems very unusual, doesn't it? Or maybe not, but it has been going on every winter for the past 4 or 5. And of course, this gentleman in the Congress pointed out that it's freezing, therefore the Earth isn't getting warmer, and he collected this snowball from the Capitol steps just to demonstrate what I think is his ignorance. And here's a different view of that. Here you can see how it's warm on this part, and that warmth extends up into the Arctic Ocean, all the way over to Europe, and it shoves this cold air mass down like that. And it's warmer on this side and warmer on that side. Sometimes, of course, we get some problems with too much warmth and too much water. So let's go back to our Oakland area and Lake Merritt. Here is the temperature range, again, from 1860, and it's the same thing. The gray areas are air bars, and then it gets much better. So Oakland has increased from, let's say, 14 degrees, sort of average temperature, to more than 16 degrees. This is not terribly surprising that it's only increased by such a small amount when you look at some of these other maps. But we are in a very ideal situation along the coast. We're protected by the oceans and about the upwelling in those oceans offshore to a certain temperature range. But global warming is overtaking us a bit. So let's look at some of these tropical storms. Believe it or not, we get to see them. Here shows how the oceans are getting warmer since 1950 on to 2020. And 3 different laboratories have demonstrated that we're now well above the 71 to 2000 average. And you can see how much right here. That means that the oceans, which collect about 90% of the CO2 contributions of heat, are becoming huge heat reserves. And with that comes hurricanes. This is Hurricane Odile. And you can see that here's the tip of Baja California, just at the upper left of the hurricane. The hurricane originated down off western Mexico, and it moved up the eastern Pacific, as these hurricanes do, and it hit Baja California and caused a great deal of damage to the tourist areas of Cabo San Lucas. But it continued up the coast, showing here, that picture would have been taken at the dot just off the tip of Baja. And then Odile continued up, running right up the peninsula until about a quarter of the way down. And then it took a right turn off into continental Mexico. This is not unusual. We get not a hurricane every year, but a lot. So the pattern in hurricanes from the East Pacific, and I'm getting to why it's important to us now. Odile was here. A lot of them go up the Gulf, sticking in the water, warmer water, and they all go up into Arizona and Nevada and create monsoonal rainstorms. But there's a group of them characterized by Hurricane Javier in 2004 that stood offshore of Baja California in the Pacific Ocean. It was a time when there was no upwelling, so the water was warmer, and it continued up about at the border with the US at San Diego. It changed from a hurricane, from being called a hurricane to being called a tropical storm, and it went on up off San Francisco and caused some consternation to ships, fishing, and so forth up there. Even though it wasn't a hurricane, it still had a lot of power. So we can expect that that kind of thing may continue to happen in the future. And this sort of summarizes all the hurricanes in 2014 in the Eastern Pacific. And you can see Odile going up the Baja Peninsula. You can see another one hooking around and going into central Baja California. But a lot of these go out across the Pacific, and the lower one went over to Hawaii. The interesting one to me is the one that takes a hard right after getting out in the central Pacific and then goes all the way to Alaska. It could be tracked that far. So we don't know where these things are going to go all the time. But we used to have a hurricane outfit that tracked this stuff. So let's quickly look at ocean acidification. I mentioned that CO2 in the water reacts with water and carbonate to produce carbonic acid. And that then causes the dissolution of the shells of the snail, for example, on the upper left. And you can see how it disintegrates it down until there's just an organic membrane left. And that's what we mean by ocean acidification. And they're having particular problems in some lagoons, like at Drake's Bay, where they had oysters growing. They're now unable to grow some of those things, I'm told. And all of these things are affected by that. So that we don't have any of these in Lake Merritt, but you may want to eat some of them sometime. So let's stop and look at sea level. Here's that diagram showing the sea and the shore lines from 13,000 years ago to 4,000, and then the modern ones. You can see how this has risen. This is just the start of sea level rise. This is a big sea level rise. But I wanted to remind you because that's the start. And then I want to point out that this is San Antonio Creek, later called Lake Merritt. And this is in 1857, and it was a slough that was connected to San Francisco Bay through this channel down to the one that goes from left to right, which is now the harbor estuary. And that's the San Antonio Creek. And it was a tidal slough with mud and marsh and estuarine biota, birds, mostly ducks, and sewage dumped into it by the growing city of Oakland. Overall, it was pretty stinky. And as a result of that smell, Samuel Merritt, mayor of Oakland in 1869, decided to build a dam across the mouth of what's Lake Merritt now, where the arrow shows it at 12th Street. And the dam was to catch high tide water and not let it get out, and that would flood the getting too old here. The slough. So in 1869, they started that. They called it Merritt's Lake right off the bat. And then for some reason that nobody seems to know, about 1874, it became Lake Merritt. So Lake Merritt was apparently a pretty nice place. Samuel Merritt thought it was. He built himself a house along the edge and started building other houses and built them up so that there were a whole bunch of them. I can't remember exactly how many, maybe around 20, of which only one remains, the Stamford Cameron House. So there was a whole line of these mansions along the edge of the lake, including Sam Merritt's house. And what Merritt discovered is that people would go out onto the edges of Lake Merritt and shoot ducks. And a lot of the pellets from their guns were hitting their houses. This annoyed him, so he went to the legislature and got the legislature to make Lake Merritt a wildlife refuge in 1870, the first one in America. That did stop the shooting at his house. And they celebrated this just in 2020. So here's recent sea level using 23 tide gauge records from 1880 to 2010, and it's risen about 20 centimeters in that time period. The red line up here is satellite measurements, and the other ones are from tide gauges, but they correspond at this level here. Now, you may remember, because I was absolutely shocked when President Trump said that sea level would not rise more than 1/8 of an inch, which I figured out is 0.31 and something centimeters in 300 years. We need somebody, a deeper thinker, somebody who appreciates science. But his appreciation of science is going in the wrong direction, as is his appreciation of what's happening with the climate. So this is Glacier San Rafael in Chile, and it shows the dates of the ice on the rock. I wrote those on there. And in 2009, I visited this site, and the 2000 level was marked by somebody else. And then today's record is back about where not quite as far as where the piece of rock sticks out. The interesting thing is that this glacier used to extend all the way out into the ocean along the coast of Chile. And Darwin even commented on how the glaciers extruded into the open ocean on the voyage of the Beagle. So as you see this glacier coming down, it forms on the polar ice cap of Chile on land, and it stays on land all the way down to the back end of that little shelf you see there at about the 209 level. And at that level, it starts to float and break up. All the ice from there on contributes to the rise in sea level. Now, imagine this happening in even a larger situation like Antarctica. Here I have superimposed the United States at the same scale on top of Antarctica, because Antarctica is 1.5 times the size of the United States. And on the diagram, the brownish colors show the areas where water or ice are warming and where ice shelves are breaking out, like the former Larsen, the Willets up in this area. The Thwaites Glacier is back in here, and that one is a huge glacier. It's grounded as it comes down into the ocean. It's grounded there, and it can't go any farther until it becomes ungrounded. And that's happening right now because warm seawater goes in underneath that glacier. And as it melts the bottom of the glacier rises. And of course, it's also melting on top. And when it pops loose, it may rush out into the ocean in what we used to call galloping glaciers. This one could bring a huge amount of ice, and it could do it very quickly. We don't have enough data to predict when or how it'll come, but a worse scenario might be very quickly sending tidal wave after tidal wave around the country, raising sea level 20 feet or so. So here's ice in the sea level rise. East Antarctica, it has about 214 feet of sea level rise embedded in it. It's going to take a few hundred years to melt East Antarctica and get the ice off of it. West Antarctica, however, has big intrusions like the Ross Sea and some others into it. And the Antarctic Peninsula sticks up to fairly high from the rest of the Antarctic continent into warmer water, but it's only 1.5 feet of sea level rise. The big ones then are Greenland. If it all melted or collapsed into the ocean, it would add almost 22 feet, plus West Antarctica, and you're looking at 10 meters of sea level rise with those two. Anyway, the total of all of these, including Greenland and all other ice, on the continents is 265 feet by this calculation. I've seen some other ones that were 280 feet, for example. A lot of this stuff needs to be figured all the time. Well, here's what projected effect of rise in sea level around our own area. It shows the current Bay Delta level in dark blue. You can see it goes up into that tree-like branching affair in the valley. And then 1 meter rise in sea level is the darker blue, the next dark blue, and it goes up and spreads out around the delta. And then the next one is a 10-meter rise in sea level, and that is so great that it goes out, flooding the valley all the way up past Sacramento and all the cities up that way and down south, Stockton and Tracy. That'd be a big deal, and it may happen. Maybe not in our time, but it could. There's a lot to be worried about. So sea level rise in Oakland has been calculated, and this is from the city of Oakland. And here you can see in lighter blue, the San Francisco Bay color blue. That's the current mean high water. The darker blue is a 72-inch sea level rise. And then the yellow up here around Lake Merritt, I'll show you that a little bit better, is also 72 inches. That's 6 feet sea level rise. So let's take a quick look at Lake Merritt. I've just tried to magnify that from the previous diagram, and you can get a good impression of where they think sea level will rise and cover up areas here. And that's just sea level rise. It doesn't say anything about tides or winds or anything else. That's just sort of static sea level rise. And the city worries a lot about that. Now, I want to point out on this geological map, the yellow in the area right along the coast, down on the lower left, you can see Lake Merritt. To the right of that, if you go down and over and up above it, it's marked QMT. That means it's a quaternary deposit, and that was formed at the 125,000 year event, sea level rise. And you can see that marine terrace almost everywhere in the world. Shows up great down around Newport Beach and south of there. You can see it up the coast, and you can see it right there at Lake Merritt. All of Adams Point is marine terrace. Most of the side of on the right side is marine terrace. And then there's marine terrace stuff stuck in the other places around. So that's what you can expect if sea level rises 8 meters, which is about 27 feet. So we have had a lot of flooding in Lake Merritt. It's not all been because of sea level rise. That doesn't help. But when it floods, we had a big flood in 1962 and 2022. These pictures that Katie gave me, and these that I copied from the newspaper, show those two floods. And of course, the tide is a big factor, and we see that happening in the past couple of weeks. Here's Lake Merritt with king tides, increasing sea level retention in the lake. And when winds and waves get to working on this, that's when they get destructive. And here's another view taken by Adrian of the bridge, people sleeping in it, I guess, and part of the tidal. So here's world energy consumption by source from 1990 to 2040. And you can see that gas, diesel, and other liquid fuels, and natural gas and coal are still going to be the dominant sources of energy and contributors to CO2 and other greenhouse gases. Wind and solar have been making a big increase, especially around 2020. They began to increase and really jumped up. That doesn't show up in this graph, which was done in 2012 to do these predictions. But wind and solar in particular have been greatly responsible for this. The climate deniers say that this is a failure of greenhouse gas efforts to control because it's already topped out. That's not true. And we haven't even considered nuclear, although they talk about third and fourth generations. Maybe you have your own little nuclear reactor in your house. So the good news is that the renewables are up 33%. Bad news, CO2, CH4, methane, both increase and up to 520 parts per million. So when does this happen? Well, there are natural variations, and there's human effects we see happening all the time now. And then there's sudden releases of methane, CH4, from the Arctic permafrost, for example, and a few other places, oil wells, and the catastrophic collapse of ice sheets into the oceans might suddenly raise sea level, but we don't know when. These are all very difficult things to estimate. For example, on the Thwaites Glacier, we can't even get all the data we need. Nevertheless, the city of Oakland has suggested that you start your adaptive strategy because that's what it's going to take to live in Oakland. Start with a review of the science, look at all the risks and vulnerabilities, plan your adaptation, and then start to implement it and then monitor it. I recommend that you look up the city of Oakland climate change. They've done a terrific job, but they make their own estimates as best they can. So here's some of the effects. Here's today, 427 parts per million. Approximate warming 1.2 degrees C. Heat waves, stronger storms, glacial retreat. 450 parts per million. Coral reefs in crisis. They're already in crisis. Arctic ice often gone in the summer. 500 parts per million in the years 2040, 2060. Most coral reefs are gone. And heat waves, killing people, they're deadly. Major flooding along the coasts and so forth. And then all the way up to 800 to 1,000 parts per million when it would be a 5 to 6 degree rise. And that would be similar to past mass extinction periods. So this is a possible scenario. Depends on how fast the parts per million buildup of CO2, and that's just CO2. If you add in methane, that's another kick that makes it happen even faster. But there are some other scenarios that are slower and some others that are faster. But you are being impacted right now here in Oakland because your food production and its costs are rising. Transportation costs are rising because gasoline, it's hotter summers, earlier springs. We have less water, more drought. With more drought comes more fires, like we've had large wildfires in the mountains, in the hills beyond Lake Merritt, and perhaps ash and debris flowing down into Lake Merritt, all due to the lower humidity. And then, of course, pollen allergies, higher tides, and coastal flooding. We see that happening, well, 3 days ago, and perhaps more storms offshore. So in our grandkids' lifetimes, I worry about this, I told you. The world population will cross 12 billion, US 370 million. Petroleum will be used up, not in my grandkids' lives, probably, but in the great grandchildren's. Climate will warm 5 to 12 degrees, sea level rise 3.3 to 27 feet. Oceans are acidifying, tropical storms, more flooding, and biodiversity and abundance will decrease. And only us can help our kids. Only us can keep our families alive for their duration of several hundred years. I can trace my family back to 1600. I'd like to see somebody in the year 2300 chase back my family. But that may not happen. We have choices. We can control emissions. We can do it now, but it's not a government favorite, and it's not a favorite even amongst some people who are very positive about climate change. And then there's geoengineering. Can we suck carbon dioxide out of the atmosphere? Nobody's been able to do it yet. They can suck it out of a power plant chimney, but not the atmosphere itself. Maybe they'll get with that. Then hopefully it will solve our problems. And that leaves only adaptation. So adapt. These are things you can do now. Cut your carbon footprint. Learn about these problems and talk to your friends, religious groups, and other groups. Join a climate organization. Write your policymakers at the state, national, and local level. We see what the city of Oakland has already done. Pretty good. They're trying. And volunteer to help and work with national through local governments. But be happy and live well. And if you promote renewable energy sources like wind, solar, nuclear, and tidal energy, that may be a big help, but it has to be done carefully, especially the nuclear. You can calculate your carbon footprint. You used to be able to go to the EPA.gov website and get your carbon footprint calculator there, but I don't think that they are allowing that anymore. But just search for carbon footprint and you'll find a place you can figure that out for yourselves. So thank you very much. There's a lot to climate change that I wasn't able to talk about, but it's all important, it's all complex, but it can be dealt with in the future. And the major way to do that is to adapt. Thank you very much.
Thank you, Jere. I'm always amazed at how you are able to explain things so clearly, and I love all your slides. They're so beautiful. Will you be able to share your slides with us at some point?
Sure.
Oh, thank you very much. I really appreciate that.
Well, I appreciate the opportunity to talk to everybody because this is a major deal for all of us. And some of us aren't doing a very good job. But I've already told you about them.
It's easy to be discouraged, but to be able to meet together and to talk about it and to clarify our understanding is huge, and it's going to, if anything, hopefully make a difference for the good in the future. I know we all have some questions. Jere, can you stay a bit longer for Q&A after I do the closing slides, which will take about 5 minutes? So I want to thank everybody for being here tonight and hope to see you again in February now. So I want to thank everyone for being here tonight and hope to see you again in February. Special thanks to Dr. Jere Lipps, the California Urban Naturalist course participants, New Voices of Rising Externs, the Water Justice Fellows, Alameda County Clean Water Program, iNaturalist, Lake Merritt Boating Center, Adopt Spot, volunteers, the Lake Merritt Breakfast Club, the Lake Merritt Institute, Oakland Public Works, Measure DD, all of Oakland. Want to show our thank you slide. We are very grateful to everyone who has made our in-person and our Lakeside Chat programs possible throughout this year. They're really so grateful to them, and we count on them for continuing to grow into 2026. Want to remind everyone that Rotary Nature Center Friends is an independent, nonprofit, all-volunteer organization. Everything that we do, we don't make money off of. And we're so happy that you're here tonight. If you enjoy the Lakeside Chats, they are rebroadcast every Sunday through the City of Oakland's KTOP Channel 10 TV. Search on the city website for the most recent and current offerings. So the first 2 Sundays of the month, KTOP rebroadcasts the Golden Oldies from our now 62 different Lakeside Chats on a variety of interesting topics. And the last 2 Sundays of the month, they broadcast the current Lakeside Chat. This Lakeside Chat will be edited by our producer, Rob Lamone, and we will have it shipshape for posting on our website playlist and also sharing on KTOP in about a week. Coming up, important things are coming up. Okay, on February 6th, our next Lakeside Chat will be called Hidden in Plain Sight, The Microscopic World of Lake Merritt and San Francisco Bay, featuring guest speaker Janai Southworth from the San Francisco Microscopical Society. Looks like I left her last name off, Janai Southworth. On January 10th, that is tomorrow, our California Naturalist class is going to be hosting a morning in the march with science and stewardship activities. Drop by to take part in native plant planting, trash removal, water testing, and other educational activities at the Sailboat House March Beach at 658 Bellevue Avenue. On January 17th, we are going to be celebrating Martin Luther King Jr. Day of Service with the City of Oakland. And we're going to get rid of this because we don't need it. Yes. Okay. And we'll be doing all of these similar activities in the same place. Want to let everybody know about a wonderful opportunity on January 24th. The nonprofit organization I Love Oakland is going to be helping to clean out all of the junked and sunken boats in the estuary channel. They received a substantial grant from the National Oceanic and Atmospheric Administration to the City of Oakland, and they're involving the public in kayak trash removal, where they kayak to a beach and get out and pull out all the trash, to just picking up land trash out there at the Jack London Aquatic Center. The location is here, and you can search the event for I Heart Oakland on the internet. I'd like to say that our urban naturalist course was really wonderful in this last year, and we are going to be having another one at the end of next year. And you can express your interest and sign up on this Eventbrite location. Also want to mention that Hank the pelican, American white pelican rescue bird, is in her 23rd year and is doing okay at Lake Merritt, thanks to the stewardship of many of the local people here, including people who feed her and who keep an eye on her. You can see the full documentary, Hank the Rescue American White Pelican by Carrie Paul, which was in our Lakeside Chat 45, and it's now, you can see the whole thing there if you go to our playlist and check out Lakeside Chat 45. There's a discussion of Hank and also a documentary which won awards. If you enjoy what we do, please consider making a donation to Rotary Nature Center Friends on our website. Here is the Rotary Nature Center Friends new Wildlife at Lake Merritt calendar. Some of the photos that we featured in our musical intro, were from the monthly pages of this beautiful calendar. If you would like to order one, you can go to our website and say for a calendar when you make your payment under the donate button. We also have the t-shirts designed by Rex Burris. We're charging $25, which is about what they cost given the many different colors that are on the shirt. We would like to thank everybody, our volunteers, program participants, and our partners. Special thank for supporting our programs and video productions to the Frederick E. Hart Foundation for Educational Opportunity, to the Alameda County Clean Water Program, and to many of the other groups that the New Voices Are Rising, many of the groups that we mentioned previously. Thank you to everybody. Rotary Nature Center Friends is an all-volunteer 501c3 nonprofit advocating for the Rotary Nature Center in Lake Merritt Park as an interpreted education and science center for all the people of Oakland and as a steward for the Lake Merritt Wildlife Refuge. Thank you. We will now return to Jere. So at this point, we usually ask people if they would like to ask a question, please to raise your hand and we'll call on you, and then you can unmute yourself and talk to Jere directly if you would like to, or we can read your question if you would rather that we do that. Okay, so here we go. Let's see, Jere, are you there?
Yep, I am.
Okay. Yeah, so please raise your hand if you'd like to ask a question. Cool. And then we have great questions in our chat. So help me out, people, if you see one. Okay, I think, Jere, I asked why does warming vary from year to year, and you gave many great answers to that question, so thank you for that. Let's see what else we have. Okay, so Anthony asks, what creates the high level of CO2 on Mars and Venus?
Yeah, well, those are pretty volcanic planets. Venus right now is very active volcanically, and Mars was volcanically quite active, at least probably from when it formed, maybe 4.6 billion years ago until 3.5 billion years. And that's pretty much what generates it.
So it was trapped during the formation and is now somehow through volcanic processes is being released into the atmosphere?
Yeah.
Thank you.
And then on Earth, we do the same thing. The CO2 normally in geological time comes out of volcanoes, and then it combines with rocks and gets degraded there chemically. It reacts with things there. We also have a huge biology that absorbs CO2 and utilizes it in one way or another. And CO2 is sequestered in the oceans in a huge way. Mars doesn't have any oceans. Maybe it did more than 3.5 billion years ago. And I've written about that too. But Venus is just too active right now. Whatever happens to it, it just stays in the atmosphere and continues to accumulate.
Thank you. Continuing, Anthony asked, you keep hearing about carbon sequestration as a viable way to reduce CO2 in the atmosphere, but is it really effective, especially if we keep clearing forests and other things that negatively impact the process of sequestration?
Yeah, well, I think the thing that's going to interfere with that more than anything are the liquid fuels, liquid carbon fuels, gasoline, diesel, and so forth that are burning. And we will need to continue to burn that. We just don't have enough energy being supplied at the moment. So it would be nice to see those curves on a downturn, but that's being impeded by, as you know, the deniers and people who are excited to continue making money that way. But it'll happen sooner or later. They'll run out of gas, run out of oil sooner or later, probably later. And we just don't have a way of really sucking it out as far as I can determine. It's not my field, but I do try to keep up with it. And the last time I looked in a month ago, there were no big winners. Just getting it out of the chimneys of any big firing thing like an electric generation, and then they would just pump it back down into the ground where it sequesters. Next.
Okay, please raise your hand and I'll call on you. I want to make sure. Oh, here's an interesting question. Do we need to worry about oxygen depletion in the atmosphere?
No. The oxygen in the atmosphere has been generated by life.
Yeah.
So as long as we have living things, we ought to do pretty well. I mean, plants.
So it's roughly 20%, right, at the moment, and
Yeah.
And the living things would be our photosynthesizers, plants, and plankton, of course, phytoplankton, and so forth. Yeah.
Yeah. They use CO2 and break out the oxygen, and then it gets transmitted to the atmosphere that way.
Let's see. Yeah, this is let's see, awesome. I wondered if you wanted to, I've been curious about the uptick in the 1950s, which some people say is the start of what should be called the Anthropocene epoch, and how that might have been related to the takeoff of the Green Revolution and industrial fertilizer production, which.
Well, certainly after World War II, maybe even a little bit before that, everything was being produced in such a way that it increased the CO2 fairly rapidly. And I think it would be interesting to see what the war did to track CO2 over that period of time in detail, like week by week. There's many ways to screw up the climate.
Please jump in, everybody. Join the conversation. You can ask something off the top of your head. It's totally okay. I always do.
Well, I see Brent Mishler said that plants take up CO2 and give off oxygen. Can you tell us about that, Brent?
Yay, plants.
Yeah.
Jerry and I talked together, and Jerry was always denigrating plants. So I'm just putting in a plug for plants.
As opposed to the phytoplankton? Or
Well, they do too. Yeah.
Yeah.
They're
well,
the
yeah.
same sort.
I guess the proportion of the oxygen in the atmosphere has been, colloquial allocated to the different kinds of photosynthesizers. I was wondering if you had thoughts about that.
Plankton is very important, and this gets into ocean health, which Jerry was talking about. About 50% of the oxygen and the photosynthesis happens in the oceans. It's not all about the big land plants we see. It's diatoms and dinoflagellates and even blue-green bacteria.
Yeah.
So ocean health is really important for photosynthetic, continuous as well.
Yeah, the Earth never had its own source of oxygen until life evolved. And then life was around for a long time. I think about 1 billion years before it began producing oxygen. They were mostly methanogenic bacteria, we think, at that time. And then something happens, some bacterium got the photosynthetic genes or whatever, and all of a sudden there was a huge oxygenation event. I think that was about 2 billion years ago.
2 billion, yeah.
Pardon?
I saw a great bumper sticker in Berkeley that said, the atmosphere brought to you by blue-green algae.
Right.
Yay.
Blue-green algae are bacteria.
Yep.
And they make many bacteria when they grow in mats and stuff, they actually get preserved in the fossil record. So we can see some mats that were preserved around 3.5 billion years, but they didn't get to produce oxygen. So they must have been methanogenic or something else. And yet they made the mats that were preserved. We don't get those methanogens until, I get rid of them as a producer of oxygen until I think it was 2.5. I have it written down somewhere. That's another project.
Well, what about the takeoff of AI and the amount of energy that's required to run the various centers that they have? Is that going to be a problem?
I have been reading a lot about AI in every magazine, from Science to a newspaper, and all the good things and even more of the bad things. And of course, the electrical demands of their data centers is enormous. It'll have to come from, we've got all the sources that they can choose from right now. And I don't know what they're going to choose. But I think AI is a great tool. I like it. It's like anything, a car is a great tool, but you can't drive crazy. And so is AI. You can't be crazy with that either.
So Deirdre brought up the rise of plastics in our lives, and of course those are based on petroleum products, which will also be, generate carbon dioxide when they're burned and when all those the processes involved are done, as another reason for an uptick after World War II. I'm trying to remember of plastics and when they really took off.
I think the other thing you have to remember is our population has been booming. I mean, we're at 8 billion people now, on Earth, and we'll be at 12 billion soon, and all of them require some energy.
But we are the big users, and we are historically the big CO2 emitters.
Well, that's true. But China and India are coming up big.
Mm-hmm. Yeah.
They're all hot on AI, and they're using that for all sorts of things. I see there was a controversy about AI writing prescriptions for people today. As far as I'm concerned, they can write out my prescriptions. It's probably faster than waiting for the doctor.
Yeah. But then, then there are other social and economic processes at work determining the availability of that, and political, as we know. Jasmine has a really good question about Lake Merritt's tidal behavior. To what extent is it controlled by engineered structures? Is there still a dam? And if controlled tidal schedules would benefit the oxygen level? That's a great question, Jasmine. And so I would refer you to the city of Oakland's. I can try to put it into the chat. They have and also the water boards has a dashboard that shows the water levels in Lake Merritt, which are controlled not only by opening and closing of tide gates, but also by input of rain and runoff from the city. But we can see that the tide gates have been open. There was a period when they were like back in the earlier history of Lake Merritt where they were closed like practically permanently, but they're open frequently now, but maybe not frequently enough. We've recently had some very low dissolved oxygens at the bottom of Lake Merritt that are concerning. And there are those great pictures that Jere showed and that Adrian took some great pictures of the incoming tides during the king tide period and coinciding with a period of rainfall and runoff from the local landscape, resulting in very high levels of water in the lake, which potentially threaten valuable human infrastructure. So all of those things are happening. I think the concept that the lake has a dam that is permanently closed for long periods of time is not accurate in the current time. And you can check those locations and get a sense of how often it's open and closed. It is closed some of the time to protect infrastructure and human stuff. Jere, you want to chip in on that too?
No, I think you guys are the experts on oxygen in the lake.
I don't know. I think it's an evolving understanding, but I just want to say that it's been fascinating. Maybe this is a good time to mention that our Lakeside chat in December, we had Eli Kirsch from the Lake Tech Corporation who talked about the buoy system and the various projects and how they're changing and in response to the analysis. I will definitely in the post-chat letter give you a link to where you can read about what they concluded after 2 years of very fine-grained observation of water quality parameters in the lake. And it's fascinating, and it's certainly not, there's a lot to learn. I think that was one of the basic conclusions, is there's still a lot to learn about, what dissolved oxygen is. Is it a problem that needs to have immediate address, or is it What could we do? How does it relate to the once the big fish kill in 2022, which has not happened again since that time? What's going on here? They're taking a slow, measured approach to understanding, and I think it's really great if the public takes interest in that and even participates in water testing and observations related to it. So
well,
I don't want to.
estuaries are just hugely dynamic places. And I don't think you're going to be able to treat Lake Merritt with one strategy. It has to be a sequence of strategies, most likely. I made an interesting observation with foraminifera, these single cell organisms with shells. They live in Lake Merritt, so we studied them. They don't like to be in minus oxygen or low oxygen environments. And I thought we'd find them all over Lake Merritt. It looks so perfect. Nope, they were only around the edges, like 1 or 2 feet deep. Because below that, at the time we sampled in 2003, I guess the lake was deoxygenated or super oxygenated. I don't know what it is. Anyway, they need oxygen and couldn't live there.
That's fascinating study. So let's make sure that everybody, these are great comments and discussions. Thank you so much. I will definitely save all of them and put some of them into a post-chat letter for everybody. Does anybody raise your hand if you'd like to mention something here? Okay, I wanted to end on the note of to thank Jere for telling us the long and the short of climate, of global warming, and to kind of put our lives in the context of the huge history of the Earth. That's really such a contribution to my understanding. I've always learned a lot at Lakeside Chats, and this is one of our really good ones. And I want to thank you for that. The people who attended the last one and are waiting for the recording, we are working on it. And we had some technological glitches on that one. We are working on it and hope to get something out, or else to have Eli back, because things are changing all the time at Lake Merritt, even in this context of broader change, the history of the Earth. It's all great to be able to follow it and to have you guys come here every month. So I would like to make sure that everyone has had a chance to make a comment. And if not, let's just all say, thanks you so much, Jere, for a really fine talk. And I really look forward to sharing your slides and sharing the recording with everybody, and really getting the message out that you articulated so well. I really appreciate it.
Yes, well, you should. What I did was to put together a lot of thoughts, and so it's not very deep, but at least there's some angles maybe you could follow up on. Plenty of websites. Just ask climate change, and you'll get more than you can handle. And there's a huge number of books, and some of them are written quite clearly. That would be very helpful if you want to follow up on some of this stuff. It is complex, but it's very, very important for us. Thank you very much.
Hopefully, some of our young people and our middle-aged people and everybody who's interested can follow up, and because there's really room for everybody to ask questions and to help to provide some of the answers. So anyway, thank you again so much. Okay, everyone, I think we've reached our end of our program. And I want to thank everybody for being here. This was great. I appreciate all of you. And I hope you will come back again. We have a great program coming up in February. We are brushing up on our skills here, and hopefully it'll go smoothly, but whatever, it was really great and really appreciate Jere and all of you. Take care and have a good weekend.